Thanks very much. Yeah, so I'll be talking about Grind. This is the new automation for Lean that we've developed over the last year. Uh, we started work on it early in 2025, and some version of it has been out the last couple of months of 2025. Uh, I'm not going to give you a tutorial right from the beginning of Grind. I'm going to show you a few different things about it. Um, but just to get us all started, grind is intended as a general purpose tactic that is mostly a finishing tactic. You call grind and it either closes the goal or fails. We'll talk about some exceptions to that as we go. The basic idea is that it keeps track of a shared whiteboard of facts, and the basic thing it does with these is keeps track of equalities and efficiently merges equivalence classes of terms. And then using those equivalence classes, it very efficiently instantiates theorems that it thinks it's meant to be using based on the terms that it's seen so far. But it also keeps track of other facts, not just equalities between terms. And we'll come, I guess, to other uses of those facts in a moment. You can think of Grind as an SMT solver, but that's native to Lean, that's designed to understand the dependent type theory and type class inference used in Lean. It's not intended for gigantic goals. You shouldn't think that Grind is something that you run for hours on massive goals with thousands of variables and thousands of facts. It's intended for smaller goals, but it is intended to be quite general and quite broad on those goals. Okay. As well as just these basic properties of merging equivalence classes and instantiating theorems, it also has a notion of custom solvers. These all collaborate using this shared whiteboard. Then the custom solvers are notified when new facts arrive, and they can decide whether those new facts are relevant to them, and they can maintain arbitrary internal state as grind works, and new facts are discovered. And the custom solvers can add facts back to this shared whiteboard. It can they can just add false back to the shared whiteboard, which finishes the proof by contradiction. But they can also add back other facts, equalities between things, or arbitrary things. So just as examples of some of the most important custom solvers available at the moment, there's a model-based algorithm for integer linear arithmetic. So if you are used to using omega in Lean, there's now a replacement that's model-based built into Grind. There's a Grosvenor basis algorithm. There's a linarith solver for inequalities in ordered modules and ordered rings. There's efficient handling of associative and commutative operators, although more features are still coming on that one. And in principle, at least, it's user extensible. We don't quite have this fully demonstrated yet, but the intent is still that users in other libraries will be able to plug in additional solvers and use these seamlessly with Grind. Okay, I think probably lots of people in the community have already seen a bit of Grind and have been seeing what's going on. Here's just a few random examples of people being happy with it. We're happy when people are happy with Grind, but we also know that there's lots more to do, and we're keen to work on the things that people want us to work on with Grind to make it even more useful. There's a nice little quote here from Terry Tao about Grind, where one thing that he points out is that Grind is really useful because of this fact that it either solves the goal or doesn't, and rather than transforming a goal into a possibly complicated and possibly unhelpful new goal, which is great. And it is very convenient that you can just quickly try Grind on a goal. But I do want to spend some time today pushing back a little bit against this idea, because the real superpower in Grind comes when you try Grind and it fails, and you work out why it failed, and you add annotations or patterns that enable Grind to then do better. And I want to show you a little bit, at least, of that process. Okay, um, just some little demos here. I think actually I should say the slides have been posted on Zulip, and if you open this up the slides yourself, uh, most of the little code snippets here are clickable and should open up live.leanlang.org where you can play around with things yourself if you want to investigate any of these examples further or see what's going on. Okay, here's just a little example of the sorts of things you can do. You can teach grind about when to instantiate theorems. And so this first sentence is just telling us that we can set up grind so that whenever it sees the functions cosine and sine defined in MATLib, it adds this basic fact about trig functions to the blackboard. And then the Grobner basis module in grind will automatically wake up because it sees that this is a polynomial, and it will then do Grobner basis reasoning. And so goals like this uh, work by a two-step process, a generic mechanism that where grind notices that trig functions appear in the goal and instantiating this theorem, and then the second step is that the Grobner basis algorithm handles things. There's many algebraic tricks built into some of these solvers. Here's an example of the Grobner basis piece of grind working in a semi-ring. Under the hood here, it's embedding this problem in the additive envelope of that semi-ring and managing to use a Grobner basis algorithm, even though you might not have immediately expected that it could do that. Okay, just another little example. This is just something about solving goals in linearly ordered vector spaces. We added this to grind basically because Terry at some point mentioned that he wanted it. This wasn't available with the linearith that used to be in, well, that is still in MATLib, but it's an example of the sort of solver that you can relatively easily add to grind. Okay. Now, when it comes to this idea that grind either succeeds or fails, one of the first things to say is that when grind does fail, it gives you some quite detailed failure diagnostics. And I do encourage everyone to play around with these and try and learn a bit about what they're doing. I accept the charge that the documentation for these diagnostics is not nearly as good as it might be, and it remains perpetually on my to-do list to make that a bit better. But just as a quick overview, this is the sort of thing that you can see in cases where grind fails. There'll be these various reports with these arrows that let you drill down inside, all of the asserted facts it's seen so far, the true propositions, the false propositions, the equivalence classes that it's identified so far. And then often you'll also get a report from one of these solvers about the internal model that it's built. And often it's very, very useful to look at these models that come out in the failures, because it's possible to see something wrong about that model. There's nothing wrong about it from the point of view of purely the linear constraints, but you might be able to see something that is inconsistent with nonlinear things going on in the problem, and that can often give you good clues about additional facts to pass to grind. Okay, we'll come back to looking at these failure diagnostics a little bit later. Okay, we're still working on many things to do with grind. There's while the standard library in Lean itself has fairly thorough annotations by now, we're still tidying up some loose ends. MATLib still has an enormously long way to go before it's fully annotated, and of course downstream libraries even more so. And I'll talk a moment about tools to both help add those annotations and to help avoid the need for them. But this is an important thing to remember, that grind will get more powerful as we add these annotations. And of course, we're still thinking about adding more solvers to grind. We think it's already a pretty big deal already. It does solve many, many tedious goals just by calling grind. And something that I'm really excited to see is AI agents starting to learn grind, hopefully in the very near future. We know that they already made significant use of things like n-linearith and omega, and I think there's every reason to expect that we'll see AI agents which do proof search themselves using grind. And I think this is going to work really well. Grind is just really efficient at doing the sorts of proofs that it does compared to the nonsense of generating proofs by an LLM and passing them through Lean to see if they work or not, and backtracking and trying again. So we really hope that Grind will make a big difference there to the effectiveness and speed of the AI proofers. Okay, I want to jump into a few more advanced topics about Grind while I have the time, because I know that people have been complaining about the fact that there's not so much documentation and tutorial on some of these things. So I want to advertise some of the new things. One of the first things is this interactive mode for Grind, where instead of just writing by Grind, you can use this grind equals greater than symbol, which then dumps you into this interactive mode where there's an internal tactic language that allows you to control Grind. Grind itself is effectively just a macro for entering grind mode and then calling the finish tactic. The finish here being an internal grind tactic. And finish is essentially something like a combinator repeat, followed by this combinator first, and then some internal things inside grind, where here solvers is just something that calls one at a time all of the solvers like Cutsat and Grosvenor. Of course, those solvers each maintain their internal state during the repeats of this loop. So these solvers aren't just waking up from scratch each time, but we're sort of calling into them to remind them that there might be new things for them to do. We might be instantiating new theorems based on the current grind state. We might do case splitting and then make something more complicated model-based theory combination, which I won't talk about today. And in principle, although in practice it's still a little bit awkward, you can replace these top-level control loops that affect how Grind deals with things. But you can also, but the really useful thing is that you can give Grind hints inside this mode. And so I'm just going to jump to a little example of how inside this Grind mode we can use the have command. Hopefully this is now going to work. Does everyone see a session
Yes.
at? Yeah, great. Okay. So, okay, well, first of all, just a quick puzzle for anyone who's bored, doesn't want to hear about Grind. If anyone knows a MATLAB free proof of this fact that isn't too long, go away and think about that. Okay, so now on to our example. What have we got? We've got five natural numbers, some simple inequalities, a equals b and b equals c, a slightly less helpful one, c squared equals d squared, and finally d equals e, and we want to prove that a equals e.
Tim,
Uh,
you, Tim, could you make it a bit bigger, maybe?
yeah, sure. How's that one?
That's better.
Okay, great. So grind itself out of the box doesn't solve this goal. What we can do is jump into interactive grind mode. Now, uh, when you use the have command inside interactive grind mode, the default is actually just to write a statement without giving any proof. And this tells Grind, please check that you can prove this statement given what you know already. So it's a great way of verifying that it can get to certain intermediate states in the proof. There's then a whole query language for looking at the grind state. And in one of the later parts of the talk, if I manage to get there, I'll show you some more. But a very basic one is show equivalence classes, where you give it some term, and then it tells you all of the equivalence classes it knows about that involve that term. So we can see here that it's managed to prove A and B and C are equal, but of course it hasn't made the jump across this one. Now we can also use have in a different mode where we give it new facts, just colon equals and something in term mode. And so here I'm doing something a little bit funny. I'm calling grind from within grind on this new fact C equals D. And I'm showing off here this thing, grind plus suggestions, which I'll come back to in a moment. But this is a cool new tool that uses a premise selection engine under the hood to identify additional theorems that Grind should be using, even though they're not already annotated as things that Grind should use. And it successfully finds this square injective theorem that we defined higher up in the file. of course, well, in fact, it gives two different suggestions. One, a grind-only statement using that theorem, but it also gives a suggestion in this internal grind-tactic language that we could use if we want. And it's probably no surprise that actually I can, if I wanted to, delete this whole have statement. That instantiate only thing in the internal grind language can just become a step in this proof. Uh, and notice that either with the instantiate only or the explicit have statement, uh, the proof is actually done at that point. As soon as we add this have statement, grind automatically saturates the equivalence classes with this new thing that it learned, and it successfully proves that A equals E. So, of course, here's another proof using the same using this square inj that grind plus suggestions found. But let's go on to another sort of use of have. Uh, Here, what have
So,
we got here?
Kim,
We've got
may I ask you
yeah,
a quick question? So,
yeah.
this grind square brackets sqinj, is that shorthand for grind instantiate only and then the things in the square brackets?
Yes, pretty much. I mean, we can change this to, well, it's not instantiate only, it's instantiate everything.
Ah, right. Yeah,
Instantiate everything you would normally instantiate it, and additionally instantiate this. If we
got it.
instantiate only, well, in this case, actually, I guess it's the only theorem it grind needs, but yeah, the instantiate only commands will not go and
Yeah,
look
of
in the
course.
library for annotated things.
Yeah.
But yes, uh, it, unfortunately, it's not literally implemented as a macro that expands this to the instantiate only, but it's pretty close under the hood.
Okay,
Okay,
thanks.
here's another little problem, a nonlinear inequality. Those who have already been exercising grind will be well aware that it doesn't really deal very well with nonlinear inequalities at this point. Uh, Something that we're definitely planning on working on. But this is just a nice little example that by going into grind mode, we can guide grind along. Here, although grind couldn't finish immediately, we can write have statements without a proof, which just tells grind, please go and see if you can prove this fact, given what you know already. And then it manages to prove that just using a Grosvenor basis argument from this hypothesis. And then after we've given it the clue that this is an interesting intermediate step, grind will finish the rest of the way. So yeah, sometimes you might find that it's possible to write proofs where there's a little sequence of halves with no proofs, just showing grind the stepping stones.
Sorry, Kim, another question. Why do we need the finish here and we did not need it in the other example?
Yeah, so here, something that grind just does automatically and without you ever asking is saturating the equivalence classes, combining equivalence classes as soon as there are new identities. So as soon as grind obtains this new fact C equals D, this equivalence class that we saw here expands to include D and E uh, without us having to say anything. But here, something quite a bit more complicated is going on to finish the proof. We actually do the case split on this OR and then use the linear arithmetic solver. Uh, we could probably do this ourselves, actually. I don't know. What do we do? We do cases next to do the case split on the next thing it can think of to do cases on. And then I think we probably just write linarith, which is not MATLib's version, but the built-in grind tactic. And there, that worked. And that's effectively all that finish is doing in this case. Okay, I better jump back and get a move on. You can see more examples in this other file if you want to have a look at those. I talked briefly about grind plus suggestions. This is pretty cool. There's a generic backend for these suggestions that libraries can configure however they like. We give you an out-of-the-box solution using this sine qua non algorithm, plus suggestions drawn from the current file. There's still a lot of work to do in optimizing this out-of-the-box solution, but it already does some pretty cool things. Let me just show you this one. Hopefully, there we go. Find the lemma that I wanted to go look for. Okay, so here's some proof. I don't know, it's 8 lines long or something. Grind can't do it. Grind plus suggestions apparently can. There's no goals to be solved. We can ask Grind what it actually found when it used that premise selection engine, and it gives us some suggestions. Let's pick that one, and we get a nice little grind-only proof. And even better, if we hover over these theorems and have a quick look at them, they're actually pretty reasonable things that maybe you should just teach to grind in the first place. So let's just add those here. At which point we can just turn this into a proof by grind. Maybe better leave a little to do here. Move these to their appropriate homes. Okay, nice. So the point here is that grind plus suggestions can sometimes be very helpful, both in showing you how to finish the proof, but also identifying potential new attributes. And we really hope to have a sort of virtuous cycle resulting from that process. When you write grind plus suggestions, that hopefully gives you some proof, grind using theorems X, Y, and Z. You then notice that the theorem X is often being passed as an argument to grind, and so you realize you should add an annotation to that theorem X. And then grind plus suggestions becomes more powerful everywhere else you ever use it, because now it's always using the theorem X along with whatever additional suggestions the premise selection engine comes up with. And Leo, in a talk last year, there's links to the notes here, it describes this as a great challenge for AI agents. Don't just attempt to give the user a proof. Instead, work out the annotations with which the proof can be done purely by these automation tools now available in Lean. And I think it would be really, really cool if someone could demonstrate some progress in this direction. We've also put a lot of work into this try question mark helper tactic. You might have been familiar with the hint tactic that previously existed in MATLib. Hopefully, it's basically supplanted by try question mark. Amongst other things, it explores running grind with a bunch of different configurations, including trying grind plus suggestions. And in some cases, at least, this avoids the need to even annotate your libraries with lemmas. You'll get better results if you do the annotation, but you can get started using these sort of tricks. We would really love to run try question mark automatically for everyone as soon as they write by in a proof. There are some technical obstacles still to that, but we're thinking about it. Here's an example, try question mark, coming up with a phenomenally complicated proof of something. Some people may have already seen this if normalization challenge thing that we've been using as an example for a while, and try question mark just absolutely blasts through it. This is a nice example to click through on to live.lang.org, as it shows you how grind is very, very flexible here, and lots of slight variants of the theorem are equally easy to prove using grind or try question mark. Okay. Now, okay, I've obviously overestimated what I can get done in half an hour. I very much wanted to show you these examples. Let's see, what's the shortest thing we can do? I guess we'll click on this one. Okay. What I wanted to show you here was a process where we were going to set up a little API for well, some new gadget that you might use in a programming library. And you can see in this file the setup where there's no proofs of anything, but also no use of grind, but that outlines how you might want to set things up. And then the second file shows you how to go through, work out which grind annotations are needed in various places, and then get to a quite nice state where at the end of the file, when it's finally time to prove all your theorems, every proof just becomes grind plus locals, grind plus locals, grind plus locals. This plus locals flag is a new feature on grind, which just tells it that it's allowed to unfold any local definitions in the current file. And maybe I'll try and prepare a little offline video of these two files, so that as we don't really have time for it now. But basically, the thing that I wanted to advertise that we do in this file is make really pervasive use of local grind attributes. So these are grind attributes that only survive the duration of this single file. But they basically give grind access to absolutely everything going on in the internal implementation of the gadget we're building in this file. And these very pervasive attributes, although they're possibly scary if you gave them out to the user, because they would enable grind, they would just have grind immediately instantiate lots of facts about the internal bits and pieces of the structure we're building. As long as we keep them as local attributes, they're relatively safe, and we get this nice situation where we can prove everything effortlessly, and then on the public API for the new structure we're building, for the theorems that don't make any reference to the internal implementation details of these things, we then put grind annotations which are global and power up grind for the external user of the library. I think it is probably relatively possible to follow through these two files linked from the talk here by yourself. But maybe after the talk, I'll make some effort to make a bit more of a walkthrough than just the two files. Okay, yeah, that's all I've got there. Thanks very much.